So organic chemistry is the chemistry of carbon compounds. Shown here are a bunch of organic or carbon-based compounds that are very complex, but are molecules that you may or may not be familiar with, such as codeine, Taxol, and penicillin. Before we begin with the nitty-gritties about organic structure, first we'll talk about electronic structure of the atom. An atom has a dense positively charged nucleus surrounded by a cloud of electrons, shown here. The electron density is highest at the nucleus and then drops off exponentially with increasing distance from the nucleus in any direction. This is an example of an 1s or an s orbital. Now the 2p orbitals are different in the sense that rather than having the highest electron density at the start, rather there's a node in which there is no electron density and then it increases and then tapers off. There are 3 of these p orbitals shown here, so they have 2 lobes oriented at right angles to each other. Each p orbital consists of these lobes in the x, y, and z axis. Isotopes are important also to organic chemistry. Isotopes are atoms with the same number of protons but different number of neutrons. Shown here is the normal carbon, 12 is the mass, and here's the protons. Now here's an isotope that's carbon-14 in which you see that there is a different number of neutrons. And again, it's dependent, you can actually tell that there's a different number of neutrons because the net mass number is larger from the normal 12. Now in terms of electronic configuration of atoms, the valence electrons are the electrons on the outermost shell. And if we look at the elements starting from hydrogen going all the way out to neon, we see that they get filled up, starting with hydrogen, which is just 1s, and there's only 1 electron, so there's only 1 valence electron. Helium has 2 electrons and it's inert. And then when we go from lithium back to the group 1 elements, you have 1s and that's full, so there's 2 electrons in 1s, and then there's in the 2s, in the valence electron, there's just 1 electron. As a result, you count 1. Beryllium is again 1s being filled, and then 2s, 2 electrons. Now as we go from boron all the way through fluorine, you're going to start to fill in the p shells. This is the 2px, 2py, 2pz, and you fill them up one at a time, and then you go back to 2px, so it becomes 2px2, 2py, y and z being 1, so that you have 6 electrons and so forth. And then when you hit neon, neon has a full octet in which all of the 2p orbitals and the 2s are completely filled. So if we look at electronic configuration in a bit more detail, you have different energy levels associated with a numbering. So if it's 1s, 1s is the lowest energy, then we go to 2s, and that's above. And then the p orbitals, there are 3 p orbitals, and all of them have the same exact electronic energy state. And so when we look at how we fill the electrons, we fill the electrons according to 2 principles. The Aufbau principle, which states that you fill the lowest energy orbitals first, again, so the lowest energy would be the 1s, then the 2s. And then Hund's rule is followed afterwards, which states that when there are 2 or more orbitals of the same energy, which means that they're degenerate, here shown here as in the 2p, x, y, and z, the electrons will go into different orbitals rather than pairing up in the same orbital. So then if you had 3 electrons being filled in the p orbitals, you'd have 1 electron being put on the ps, x, 1 in the py, and the 1 in the pz before doubling up. Ionic bonding is an important form of bonding. So in order to obtain noble gas configuration, a full valence shell of 8, atoms can transfer electrons from one atom to another in the case of ionic bonding. So the atoms, once they do this, will form an ionic bond because they will bear opposite charges. And so shown here is lithium fluoride. You're going to have a transfer of the electron to the fluorine, and note that the arrow here is a half arrow. So when there's a half arrow, that means it's a one electron motion. And because of that one electron motion, you have lithium being positively charged, has a helium configuration, and then fluorine being negatively charged with a neon configuration. Now, because they're oppositely charged, they then kind of are around each other, forming this ionic bond. By contrast, covalent bonding, electrons are shared between the atoms to complete the octet. And there are two types of covalent bonding, nonpolar covalent as well as covalent. In the case of nonpolar covalent, the electrons are shared evenly across the bond. And so this is a nonpolar covalent or pure covalent bond. In the case of a polar covalent bond, the electrons are not necessarily shared evenly between the atoms. Rather, you have kind of an uneven sharing where most of the electrons are pulled closer to the chlorine, for example, in this case, versus the carbon. And so this leads to a polar covalent bond. Now this leads to Lewis structure. This is an important type of denotation of molecules that you should learn how to do well, because everything from henceforth Lewis structures will be shown as Lewis structures. So in the case of Lewis structures, for example, this is methane. It has carbon. Carbon has 4 electrons, right? And then hydrogen has 1 electron each. And so there's a sharing of the bonds in terms of covalent bonds shown here, which allows it to achieve this 8 electron octet. Similarly in ammonia has 5 electrons, in which you have 3 unpaired electrons that then get paired up with the hydrogens. In the case of water, you have oxygen with 6 electrons in the beginning, and this 1 electron gets shared with another from hydrogen and another from hydrogen on the other side. And then the last example is chlorine, of diatomic chlorine, in which you have 7 electrons and 7 electrons on chlorine, and 1 of those electrons being shared across, fulfilling the octet. Now, in terms of bonding patterns, if we look at the most elements that are used in organic chemistry, carbon, nitrogen, oxygen, halides, carbon has 4 valence electrons. As a result, it can make 4 bonds, and it doesn't have any lone pairs. Nitrogen, by contrast, has 5 valence electrons, allowing 3 of them to form bonds with 1 lone pair. Oxygen has 6, allowing for 2 bonds and 2 lone pairs, and then in the case of halides, there are 7, which allows only for 1 bonds with the 3 remainder as lone pairs. If we look at the non-bonding electrons, or the lone pairs as shown here, here are examples where you have lone pairs being shown. Usually nitrogen has 1 lone pair, oxygens usually have 2, and the halides have 3. And these non-bonding electrons are valence shell electrons that are not shared between atoms. So we've shown that you can have sharing with an electron and another electron forming a single bond. You can also have multiple bonding, such as double bonds and triple bonds. So here are some examples of double bonds. Here's ethylene, in which you have a double bond across the carbon-carbon, and if you can see, the double bond is shown as 4 Lewis dots. Formaldehyde, the same thing, C double bond O, again 4 electrons between carbon and oxygen. And then C double bond N in amine, and again 4 electrons shown there. And if we'd have 6, that would indicate a triple bond. Lewis structures are the way we write organic chemistry, so learning to draw them quickly and correctly will help you throughout this course. Now, dipole moment is also reflected in some molecules. Dipole moment is defined to be the amount of charge separation, or delta, multiplied by the bond length, shown here as mu. So in dichloromethane, you have a positive or partially negative charge due to the electronegativity of the chlorine, and partial positive charge on the carbon. This allows for separation in which you have a positive dipole moment going to the negative, shown by this mu. And this is also demonstrated by this electrostatic potential, where the red is the partial negative and the blue region is the partial positive. Like I said, the dipole moment is dependent on the electronegativities. Here's the Pauling electronegativities. It's used to predict whether the bond will be polar and the direction of its dipole moments. Since the electronegativities of carbon, hydrogen are similar, CH bonds are usually considered to be nonpolar. And so you can see that hydrogen, boron, carbon, silicon, and phosphorus are neutral. However, all the blue ones are supposed to represent the partial positive, and all the red ones or the pink ones are supposed to represent those that are going to be negative. Now, we can then calculate what are called formal charges. Formal charges, the equation is represented as the group number and subtract the non-bonding electrons and subtract half of the shared electrons. So as an example, here's a hydronium ion, H3O+. You're adding the electrons to the oxygen, and if we're trying to calculate the formal charge on the oxygen, it's 6, the group number of oxygen is 6, minus 2, right? The non-bonding electrons are 2 non-bonding electrons, minus half of the shared electrons, which are 6. Remember, each single bond is represented as 2 electrons. This allows you to get a formal charge of +1. For NO+, you have you can determine the formal charge per atom. So for nitrogen, you have a group number 5 minus 2 non-bonding electrons, right? Minus a half of 6, right? There's 6 electrons being shared in this triple bond. This leads to a 0 formal charge. But on the oxygen, we have a formal charge that is +1 because we have 6 from the oxygens, minus 2, minus half of 6, leaving it to be a +1. Formal charges are ways to keep track of the electrons. They may or may not correspond to the actual charge of the molecule. So let's do a problem. Compute the formal charge of each of the atoms in this H3N BH3. So shown here is the solution, right? You draw your Lewis dot structure with your nitrogen and your boron, and then your hydrogens filling up the unpaired electrons. And then once you do that, you have to figure out, okay, nitrogen. Nitrogen has 4 bonds, 8 bonding electrons, so the formal charge on here is going to be plus. Boron has 4 bonds, 8 bonding electrons, so the charge here is going to be minus. And so you should be able to determine the formal charges based on the equations and so forth. One good thing after determining formal charges of various molecules, you start to understand what the common bonding patterns are. So across the atoms shown here, boron, carbon, nitrogen, oxygen, and halogens, you can note their valence electrons 3 through 7. If we look at the kind of common bonding patterns when we're just looking at it as a neutral atom, boron usually has 3 bonds to boron. Carbon is 4, nitrogen has 3 with a lone pair, and oxygen has 2 with 2 lone pairs, and halogens usually have 1 with 3 lone pairs. So this is the neutral status of these elements or atoms. Now, in terms of positively charged, what happens is it'll gain positive charge when you have, in the case of carbon, one less bond or one lack of bond, and leaving it to be a carbocation. For nitrogen, if you have 1 extra bond, That'll lead to a positive charge. One extra bond for oxygen and one extra bond for the halogens will also lead to a positive charge. For negatively charged, in the case of boron, if you add an extra bond to the boron, this will lead to a negative charge. Carbon, if you have two lone pairs, non-bonding pairs, this will lead to a negative. Nitrogen, again, another non-bonding pair, negative. Oxygen, non-bonding pair, negative. And chlorine, non-bonding pair, negative. So I can't stress this enough, but you should work enough problems to become familiar with these bonding patterns so you can recognize other patterns as being unusual and warm. This is critical, especially when you're going to be taking exams in my class. You should be able to know this backwards and forwards to be able to know patterns and be able to do Lewis dot structures in your sleep. So prior to coming to class, I suggest you do a bunch of these problems because we'll be doing problems from the get-go, starting from the beginning of class. Now, resonance forms are important as well. Structures of some compounds are not adequately represented by a single Lewis structure. As a result, you have resonance forms, which are Lewis structures that can be interconverted by moving electrons only. The true structures of such resonance forms are usually a hybrid between the contributing resonance forms. So, for example, here's this molecule shown here in which you have a carbocation and a nitrogen. Now you see electrons being pushed through from the nitrogen lone pair to form another bond here. This then leads to the migration of this positive charge to the nitrogen. And in resonance structure, you have this double-headed arrow being shown and then brackets. So whenever I'm asking you on an exam for resonance structures, you should always put them in brackets and double-headed arrows and show where the electrons are migrating. So this is a resonance form of the molecule. And the combined representation essentially is a dotted line across showing partial positive across being shared across the C and the N. Resonance forms can be compared using the following criteria, beginning with the most important. 1. Has as many octets as possible. 2. Has as many bonds as possible. 3. Has a negative charge on the most electronegative atom. And 4. Has as little charge separation as possible. So if we look at major and minor contributors, the major contributor is the one in which all the atoms have a complete octet of electrons. Shown here is a resonance structure of formaldehyde. So the electrons from this double bond, or one of the single bonds of the double bond, will then be pushed up, moved here. Again, the double-headed resonance arrows. And you have charge separation where you have a positive charge and a negative charge in the brackets. So of these two, which one is the major and minor? This represents the major because you have all octets, no charge separation, versus this, there's no octet on carbon and there is charge separation. And then this helps you also figure out what the dipole moment of it is, right? There's a partial positive charge and a partial negative charge due to the charge separation, allowing you to determine the dipole moment. When both the resonance forms obey the octet rule, the major contributor is the one with the negative charge on the most electronegative atom. So shown here is nitrogen, carbon, oxygen. Here where you have charge separation in which, a charge in which you have a negative charge residing on the oxygen. Now what's happening here is the electrons from the oxygen are going to the carbon, and then this kicks off and puts the electrons on the nitrogen. Remember, carbon can have no more than 4 bonds. So then this leads to this other resonance form, which now has nitrogen, the negative charge residing on the nitrogen. Now, this is not a true resonance representation because while it does show the double-headed arrow, it's not in brackets. So again, if you are missing the brackets in your exam, for example, this would lead to points being taken off. So please be careful about that. Now, of these two, this one is the major contributor. Because the oxygen is more electronegative, it should have the negative charge. So when we look at non-equivalent resonances, opposite charges should be on adjacent atoms. So if we look at an example here, We have no charge separation. Everything's fulfilled in terms of octet rule. Now, if we have electrons from the oxygen come in and form a bond, then you're kicking off the electrons from the oxygen and leaving it onto the electrons from the single bond and leaving it onto the oxygen. This allows for charge separation, which now you have a positive charge and a negative charge on the oxygen. Obviously, this is the major. This is the most stable. It's the one with the smallest separation of oppositely charged atoms. And again, this is not necessarily in the correct convention. You should be having brackets on either side along with a double-headed arrow. So if we do a problem, the problem says draw the important resonance forms for this molecule shown here. Indicate which structure is a major and minor contributor, or whether they would have the same energy. So if we draw it out in terms of Lewis dots, we would draw out the structure here in which you have a positive charge on the carbon. Now you can have the electrons from the oxygen come in and quench that positive charge, migrating that positive charge to the oxygen. Now, of these two forms, which one is the major and which one is the minor? This one is the major. The major has octets around all atoms and an additional bond. And here in the minor structure, the carbon has only 6 electrons on it. Here's another problem for you. Draw the resonance structures of the compound below. Indicate which structure is the major and minor contributor, or whether they would have the same energy. So shown here is the molecule. Now you can say the electrons from the carbanion move and form a bond. These then push the electrons from this double bond oxygen, single bond breaks, and then puts the electrons to the oxygen, so that now the negative charge is no longer residing on the carbon, but rather residing on the oxygen. Again, this becomes your major contributor. The oxygen is the more electronegative element, so having the charge, negative charge, reside on the oxygen makes more sense here. Now, if we look at the resonance form of acetate ions, acetate ions are formed when acetic acid is in water. It's under equilibrium, so this is a different type of arrow. You see half the arrow going one way and the other way. This is called an equilibrium atom. And now when they form acetate, there's not one form but two resonance forms. So again, the resonance structures are shown with brackets and the double-headed arrow. So here's one resonance form in which this oxygen on the bottom has a negative charge. Now the electrons are being pushed to form a new double bond here, and that one double bond, or the single bond of that double bond, breaks to push the electrons out to this oxygen, so that you have this oxygen now having the negative charge. These are equivalent resonance forms, plus hydronium ion. So each of these oxygens then, this one and this negative one and this one, bears half the negative charge, and this delocalization stabilizes this ion, this acetate ion. Each of the carbon-oxygen bonds is halfway between a single bond and a double bond and is said to have a bond order of 1.5. So now that you know how to do Lewis structures, we can also talk about condensed structures. Condensed structures are written without showing any of the individual bonds, unlike Lewis structures. Atoms bonded to the central atom are listed after the central atom, so it's CH3CH3, not H3CCH3. If there are two or more identical groups, parentheses and subscripts may be used to represent them, and we'll show examples of it in a bit. So shown here are two examples, one bromo and one, ketone. So in terms of condensed structures, none of the bonds are being shown except for the ones with the heteroatom, which is the bromine and the carbonyl shown here. Ethane, CH3CH3, isobutane. Now you see CH3, then subscript is 3 with the CH. So that is showing that you have 3 of these CH3 groups around a central CH, and so condensed formula is accurately representing this. And then N-hexane, in which there are a bunch of CH2s in the middle of 2 CH3s. Some more condensed structure, diethyl ether. Right now there are 3 different ways you can show this. You can just show this CH3CH2O, CH2CH3, or you can distinguish with the bond showing O, because I had said all heteroatoms should be shown as a line. Or you can have this CH3CH2 and then bracket it into 2 by the central oxygen. Ethanol is shown here. Ethanol is self-sufficient. Isopropyl alcohol, you have 2 CH3s flanking this COH, and so that's represented here. And then dimethylamine are shown as 2 CH3s on the central nitrogen. More condensed formulas, 2-hexene. Again, the double bond is shown out here. I would like if when you're asked in exams to show condensed formulas, I would like you to show them as the double bonds or as the heteroatoms shown with the bonding rather than without showing it. So again, here's butene, acetonitrile with a triple bond being shown, acetaldehyde showing the aldehyde group, acetone with the ketone group, acetic acid showing a C double bond OOH. That's actually how I would like you guys to represent it, but all these other conventions are okay. Now this brings us to simplifying it even more from Lewis structures as line drawings. So Lewis structures just kind of draws all the atoms out. Well, you can then take all the carbon and remove all the hydrogens, and you can kind of angle it in this way. And if we remove all the carbons, the line drawing becomes just this zigzag, essentially. This is sometimes called the skeletal structure or stick figure. Bonds are represented by lines, and carbons are present where a line begins or ends, or where 2 lines meet. So here's an end, those have carbons, and then where 2 lines meet, those are carbons. Hydrogens are not shown. Nitrogen, oxygen, halides must be shown. So for an example, here is an aldehyde which has 6 carbons. So now instead of drawing it all out to make it simplified or easier, you draw it zigzag until you hit the 6th carbon and then draw the aldehyde out. So you show it. Here are some other examples where you can simplify it. Hexane, just drawing it out like this. Hexene, which is shown with a double bond in between. Hexanol, over here, 3-ol, over here at the 3rd carbon. Cyclohex 2-ene 1-one. Here you have it simplified as this cyclic structure with double bond and ketone. 2-methylcyclohexane 1-ol can be shown like this and this. This would be actually the true showing of it without showing the methyl, because this would be represented as a methyl. And then nicotinic acid shown here. The best representation, I would like you to show it as with the carbonyl and the OH shown out instead of COH in exams. Calculating empirical formulas. The following items that need to be considered when calculating empirical formulas are: you give percent composition for each element, assuming 100 grams. You convert the grams of each element into moles, divide by the smallest number of moles to get the ratio, and then the molecular formula may be a multiple of the empirical formula. For such calculations, if an elemental analysis does not add up to 100%, the missing percentage is assumed to be oxygen. And then now we can talk about acids and bases and different, nomenclatures or or concepts of what an acid and base is. Arrhenius acids are substances that are dissociated in water to give hydronium ions, or H3O+. So for example, in sulfuric acid here, in water you form hydronium ion and then the HSO4, where it has moved its H+ atom. Stronger acids dissociate to a greater degree than weaker acids. In terms of Arrhenius bases are substances that dissociate in water to give hydroxide ions, sodium hydroxide, magnesium hydroxide shown here as examples. They dissociate in water here, giving a hydroxide, here in this case giving 2 hydroxides. Stronger bases, like sodium hydroxide, dissociate more than weaker bases, like magnesium hydroxide. Now, by contrast, we have Bronsted-Lowry acids and bases. Bronsted-Lowry acids are any species that donate a proton, shown here. So all of these red are the protons being donated. Here are Bronsted-Lowry bases, which are bases that are or species that can accept a proton. So these will accept protons. And then these will form salt and water or whatever the results are. If we look at the naming of what's on the other end of the arrows, these are conjugate acids and conjugate base. A conjugate acid, as shown here, is when a base accepts a proton. So the base, the Bronsted-Lowry base, will accept a proton to form the conjugate acid. And then the Bronsted-Lowry acid will form the conjugate base because it becomes capable of accepting a proton back. And so here are the rest of the examples that you can go through in your own time. If we look at the effect of electronegativity on the pKa's, because we're looking at the acidity and basicity of things. So as you're going from left to right, you're increasing the electronegativity from carbon to fluorine. That increases the stability, right, from CH3 all the way to F-. And then also as you go from left to right, your acidity increases, right, from carbon to fluorine. Basicity, on the other hand, goes in the reverse order of acidity, in which now F- to CH3, you're increasing basicity. Size also of the atom affects the pKa. So for example, you have iodine going to fluorine, and as you're going from iodine to fluorine, you're decreasing the size. As you decrease the size from iodine to fluorine, you're decreasing the acidity. In other words, as you increase the size, you're increasing acidity. Resonance can also have an effect on pKa. So here are some examples of acids or acidities of ethanol, acetic acid, and methane sulfonic acid. So as you go from ethanol to acetic acid is exhibiting resonance structures in the acetate ion. As a result, you see a drop in the pKa, so it becomes more acidic. In the case of methane sulfonic acid, you have 3 different resonance structures leading to really strong acid. Because it's stabilizing the ion through resonance. Lewis bases are species with available electrons and can be donated to form a new bond. This is very different from the Bronsted-Lowry acids, bases, etc. Lewis acids are species that can accept these electrons to form new bonds. Since Lewis acids accept a pair of electrons, it's called an electrophile. Nucleophiles and electrophiles are defined and are important definitions because from henceforth we'll start to look at reactivity dependent on whether something's a nucleophile or electrophile. Nucleophiles donate electrons to a nucleus within an empty orbital, while electrons accept a pair of electrons. So when forming a bond, the nucleophile essentially attacks the electrophile, so the arrow always goes from the negative to positive. This point is essential, especially when we're doing mechanisms, and especially since you guys will be doing YouTubes of mechanisms. Mechanisms always should be shown where you have the nucleophile attacking the electrophile, so your arrow should always start from a negative electron source to the positive. Now, when breaking a bond, the more electronegative atom always receives the electron. And so finally, here's examples of nucleophiles and electrophiles and how you should be able to show arrows when reacting nucleophiles and electrophiles. Here's Lewis base, Lewis acid definition of nucleophile and electrophile, in which the electrons from this base go and react with the electrophile, forming that bond. In the case here, you have NH3 and BF3, actually the resultant molecule which we earlier shown the formal charge, identification of the formal charges. Electrons from the negative source. Here the electrons go to the boron, forming the covalent bond. Here is a reaction in which you have methoxide electrons going and attacking this carbon bond. Now, since carbon can only have 4 things attached to it, it has to let go of or break a bond. In this case, it's breaking the carbon-chlorine bond, and as a result of its breaking, you're showing an arrow going to the electrons. This leaves a chloride anion and a new bond being formed. Here's another way to look at nucleophiles and electrophile. Here's ammonia. The electrons from the ammonia go and take that proton, forming a bond. Now that proton needs to cut its bond with the oxygen, so that those electrons from that bond now go to the oxygen, making the conjugate base, forming this new conjugate acid. So this concludes chapter 1. Again, you should go through this presentation, go through all the problems in the back of your book, get some practice, because starting class, I'll be asking you to volunteer, or if not, I'll be calling your names so that you guys come up and answer the problems that are posted on Twitter. All right.